Okay, so let's get started. Okay, before we start the material, okay, today, okay, first I would like to tell you guys like we have a company, okay, Ding Ye, okay, 叶院长, okay, from 管理学院, okay, 就是he's here to observe me, okay, not you guys, okay, so don't worry about that, okay, so I will be the one to worry, okay, not you guys, okay, 就是我被评量的，不是你们 ，OK， 所以不用担心。So a few things to remind you, okay. First, we have the quiz last week, right? So I believe like the TA will give you guys back the graded quiz and the midterm, okay, later, okay, in between classes, okay, 就是下课的时候会把那个就是你们的期中考跟你们的那个就是那个前面的 quiz 哦，就是还给你们 ，okay. This is the first thing, okay. The second thing, okay, we will have let me think, the fourth quiz, okay, next week. Oh, sorry, not next week, okay, because next week, oh, by the way, next week we don't have classes, okay, because we have like it's a field day, okay, for our school, right? 我们有运动会 okay, so we don't have class next week. But the week after next, remember, we will have quiz, okay, the fourth quiz, okay, just want to remind you guys, on that, okay. So yeah, I mean, as you know, motivation for you guys, okay. You know, like we have won like you know, the champion, okay, in the field day, like for the past 3 years, right? 前面3年我们不是都拿总锦标冠军吗 ？Okay, so this year, okay, I hope you guys can repeat, okay, the fourth time, okay. If you guys can do that, okay, I will give you 2 points. Okay, toward the final grade. Okay, final grade. 就是期末的那个成绩加2分 for all of you. 很甜吧 Okay, 每个人加2分 Okay, so next week, okay, the field day, okay, please work hard, okay. I really hope like we can, you know, continue the trend and, you know, beat our rivalry, okay. I will not name that who our rivalry is, okay, because the thing is there, okay. Yeah. Okay. So, oh, sorry, I need to turn off the. Okay, so let's get started. Okay, so last week we finished like section 5, right? And I believe like we are in the middle of section 6. Is that right? We talk about like the row space and the column space, and I believe we also talk about like you know if A and B two matrices are row equivalent matrices, then their row spaces will be the same. Yeah, basically like because like we know like row equivalent means like those you know operations. Okay, 3 operations that you can do to the matrices. I mean, those operations are reversible, right? So it's like just linear combinations or like exchange like 2 rows or something like that. So obviously like it will not change the space that is spent by the row vectors, right? Okay, 我们上次讲过这个嘛，因为你的那个矩阵里面的，因为那个这个所谓的 row 那个 我们的那个 elementary row operation 就是 those three operations OK 一个是两个 row 就互换 OK exchange two rows or OK you multiply one row by non-zero you know factor right 就是乘上一个非零的一个某一个那个列乘上一个非零的那个数字 or OK you multiply a row with a with a factor and add that row to another row. Okay, all these three operations they are reversible, and because like the row space is spanned by the row vectors, so obviously like you know if two matrices have the same, I mean are like a row equivalent matrices, then I mean they will have the same space, row space, okay. And then okay, this one, okay. I believe we finished this this one as well, right? I just want to double check. Yeah, because this one is also very important. If A and B are row equivalent, this not row equivalent matrices, then okay, their column vectors. Okay, you know, any given subset of column vectors of A is linearly independent if and only if the corresponding columns of B are linearly dependent. Basically, when the two matrices are row equivalent, we know we have this, right? AX equal to 0 and BX equal to 0. This is like you know based on our very beginning. Okay, when we talk about those row operations are basically like the process of like Gaussian Jordan elimination, right? So basically like when you do like elementary row operations, basically like that guarantee like these two linear the system of linear equations have the same solutions, right? Solution space. Okay, but if you consider this basically means okay. Say this is A. Okay, so we have a bunch of columns. And each of these columns, okay, remember like the notation I told you earlier, okay, this A sub 1 means the column vector, right? So this is A sub 1. This is A sub 2, and so on. This is A sub N. Okay. And your X is X1, X2, Xn. Okay. And one way to think about AX would be exactly like X1 times A1 plus X2 times A2 and so on. Right? Because you know this is a very fundamental you know to the matrix operations, right? Okay, so you can sort of consider like this like AX equal to 0 as like a how should I say, like a linear combination of column vectors, right? Equal 0 vector. Okay, so if AX equal to 0, this actually means like the 0 vector, okay, with n components, obviously. So these two have the have the same solution space, meaning it means like this one and this one have exactly the same solution, right? If that's the case, think about it. Think about it, okay? Then this AI's column vectors, if this A1, A2 to AN, if they are independent, what is the meaning of independence? A bunch of vectors are considered to be independent when, if their linear combination is 0, the only possible solution will be, you know, the x1 equal to x2 equal to blah, 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 equal to xn equal to 0, right? Okay, so in other words, if this one is independent, A1 to AN are dependent, it means we only have like x1 equal to x2, x equal to x3 equal to xn equal to 0, right? That's the only solution for this equation, right? So if that's the case, then this one also have the only, that's also the only solution for this one, right? So if this one, the only solution for this one is x1 equal to x2 equal to x3 equal to blah, 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 equal to xn equal to 0, okay, for this equation, then it pretty much means like BI's are also independent, right? And also, okay, even though, I mean, previously I said like we consider all these, you know, column vectors, but the similar argument work for any subset of these column vectors. Okay, you just try to imagine. Okay, for example, let's think about like a very concrete case. 我们就想一个比较实际的例子。OK， 就像说我们现在只拿前面2列 ，let's only get like the first 2 rows。所以out of ink. So let's call this A prime. Okay, we have in this A prime we have only A1 and A2. Okay. These 2 column vectors, only these 2 column vectors. And B prime also be B1 and B2. Think about this. If A and B are row equivalent, meaning you can use those row equivalent operations to get B from A, right? So you using exactly the same order of operations, you can get B prime from A prime as well, right? 对不对？因为你想想看，就是如果原来是那个从 A 到 B， 譬如你经过某一些 operation，row operation， 就是说 elementary row operation， 从 A 得到 B， 因为你只是把一些 column 拿掉嘛，对 ，you only get rid of some columns， so I mean the same order, the same, you know, elementary row operations will bring you from A prime to B prime as well, right? So in other words, A prime and B prime are row equivalent, right? Row equivalent. And then the argument below work for A prime and B prime, right? 就是说，你现在 previously, I mean, in our discussion, originally we are considering all the column vectors. 我们原来考虑的是所有的 column vector. 那我现在是跟你讲说 ，now I'm telling you, OK， 就是从这些 column vector， 你随便选一个 subset. You pick any subset from these column vectors. OK, basically, OK, you will have exactly the same nature. So that's why, OK, a given set of column vectors of A is linearly independent, and only if the corresponding columns of B are linearly independent. If A and B are row equivalent. Okay. So with that, okay, a given set of column vectors of A is a basis of the column space of A. If only if the corresponding columns of B are a basis of column space of B, right? Because the independence imply they form a basis, right? 我们讲过 dimension 了，对不对 ？We talked about dimension in the previous section. 所以 basically like you know, from the first point we get the second point immediately. So far so good, right? Okay, y'all. Okay. So up to now, okay. I mean, I hope you guys are still with me because we finished this slide last time. I mean, starting from next slide, it'll be something new, okay, today, okay? So then, okay, the next one, okay. So now, okay, we have, before we continue, let me remind you one thing, okay? What should I say? Like, we know, like, if two matrices are row equivalent, then their row spaces will be exactly the same, right? Okay, but if two matrices are row equivalent, are their column space equivalent? I mean, like the space spanned by the columns, are they the same? This is different question, right? This is different question, okay? 就前面我们讲说是 row space if two matrices are row equivalent, their row space will be the same. This is not much to argue, okay? Very simple fact, okay? If two matrices are row equivalent, how about their column space? Are their column spaces equivalent? The answer is not necessary, okay? However, one thing we are sure, okay, the column space of two row equivalent matrices, their dimension will be the same. Okay, dimension will be the same. But I mean, so far, I mean, all the discussion that we have here never indicate, okay, the column space will be the same. Okay, that's two different things. Okay, I just want to remind you on that. So for any matrix, the dimension of its row space is the same as dimension of the column space. So this is starting to be interesting. Okay. So how do we know that? Okay. Let's consider, okay, the row echelon form. Okay, if we reduce the matrix, into a row echelon form. Okay. One moment. Let me get. Let's see. Okay. Okay, that's okay. For any matrix A, let's assume we already reduce it to row echelon form. So what is row echelon form? Oh, 谢谢. Let me just. What is row echelon form? obviously we will apply some row equivalent operations, right? Okay, and then let's get this A prime. Say A prime is row echelon form. And we know that these two, matrix A and matrix B, their row space are equivalent, right? Right? And also, A and A prime, their column space have the same dimension, right? Right? These things, we know these things, right? But what exactly is the row echelon form? Row echelon form is something like this, okay? You can go back to chapter, I believe chapter 1, okay, to check like a definition of row echelon form. That means like, for example, like if you have some leading one, okay, and it may, indent, okay. If the first one is here, the second one has to be, on the right, of the column, and all these will be 0, right? Not only here, but also all these will be 0, right? And this part may not be 0, but this part is 0. After, the beneath like the leading one. And if certain row does not have leading one, then it's empty, right? It's empty. It's empty. And you may have some leading one here as well. And say like the last few rows may also be empty. Right? Right? And the element on the top of leading one, they may not be empty. So this is not necessarily 0. The stuff above this may not be. You may have something here, and so on, right? Right. So let's consider the dimensionality of this matrix. Okay. You can tell, okay, the dimension must be, the number of the rows that are non-zero, right? With the leading one, and make it more concrete. For example, let's say we have 3 rows that has leading one. Then the dimension of the row space will be this one, and this one. Well, the row space will be basically spanned by these 3 vectors, right? And the other rows are pretty much empty, right? Pretty much empty. Okay? So the number of leading one rows is, indicate the dimension of the row space. But how about column space? Remember, I told you, okay, the non-zero elements only appear, okay, above the leading one, right? All the other places we have all zeros. So if you look at here, again, these 3 vector will span the column space, right? These 3 vector will span the column space of A prime. Remember, this column space may be different from the column space of A, but the dimension will be the same, right? Dimension will be the same. And because, okay, of these leading ones, they fall at a different row. So the only possible, say this is A1, let's say this is A2, A3. I mean, just for the sake of convenience. Okay, let's call these three column vector as A1, A2, A3. If you have x1, A1 plus x2, A2 plus x3, A3 equal to 0, you know, the only possible solution will be x1 equal to x2 equal to x3 equal to 0, because, you know, you have to make this one, this one, this one, okay, you know, at a different row place, okay, you know, multiply xi, you know, add up to be 0, right? So that pretty much force that, okay, x1, x2, x3 to be all 0, and that basically means like, you know, the dimension of your column space is 3, right? Is 3. If you have 3 leading ones, okay. I mean, here, of course, I'm using like 3 leading ones, okay, as an example, but it doesn't matter. I mean, if you have like a k leading one, okay, rows, that will also means you have k dimension is k for, you know, for column space. So you can see like the row space dimension and the column space dimension will be the same, and they will both be the number of leading ones after you convert the matrix into you know, a row echelon form. Okay. So that pretty much implies that the row space and the column space, their dimensions are the same, and so we can define, okay, a matrix, okay, its column space and the row space dimension, okay, because they are the same, right? So we call that number as the rank of A. The rank of A. Okay.我也许英文用的比较多先，因为我被evaluate， 所以我会不自主的用比较多英文。Okay, if I, you know, if there's something that you don't understand, you would like me to, you know, rephrase it like in Chinese, let me know, please. Okay, 不好意思哦，因为好像我觉得好像英文用的今天用比较多一点。Okay. So another thing is called null space. 另外一个我们要可以定义一个叫 null space 的。Okay. So A is an n times n matrix. All solution of AX equal to 0 form a subspace of Rn and is called the null space of A. We can denote that space, that null space as null A. Okay, we actually previously have like a example of doing that, if you remember. Okay, 好像有点早。这个 this one, the null space of a matrix. This one. Basically, we try to solve this with like a x, you know, x1, x2, x3, x4, and then equal to 0. And then we solve this like we have two equations, so we can use like again row echelon form. Okay, and then you know, I mean later we will, you know, obtain this thing. Okay, NA is expanded by these two vectors. And obviously, you can tell this null space is of dimension 2, right? 这个 null space 是维度是2嘛，对不对？因为 it is spanned by two column vectors. Okay. So, okay. So the dimension of a null space of A is called nullity of A, and denoted as nullity A. Okay, another notation to remember. Okay, 就是你要记得说，当我写 nullity，what does that mean? Okay. So there's one interesting thing. If A is n times n matrix, we have rank A plus nullity A equal to n. So what is that? I mean, actually, the argument will be similar. Okay, will be similar. Let's say you reduce A into A prime, which is the row echelon form. Okay. So we know like the rank of A and rank of A prime are the same, right? Okay. So what does A look like? A prime look like? We have like some leading ones, and we have a bunch of zeros, right? Right? Okay. And if we want to, because I mean, this is X, because when you consider the AX equal to 0, because this is like the formula to solve, okay, when you want to compute the null space, right? Okay, that's the formula to solve. I mean, when you want to compute null spaces. But okay, then this will be equivalent to A prime X equal to 0, right? I mean, these two have the same set of solutions, right? 它们两个有同样的 solution 嘛，对不对？ Because they A and A prime are row equivalent, right? Okay, so think about this. I mean, the number of rows, okay, with all zeros would be the freedom of your null space, right? Okay, remember how we obtain this. How we obtain this one. How do we obtain this one? Remember, here, like we make x3 to be S, x4 to be T, right? Okay, so basically the other, I mean, will be the other. I mean, they have something here, right? They have something here, and if I name this, for example, like this zero, the 0 rows, okay, the corresponding component, okay, in the X for these 0 rows to be S and T, okay, then our X1 will be, you move this to the other side, right? Okay, to get this. So that's exactly, this part. I mean, and this is this part. So basically, the S and the T. Okay, you name S. I mean, those. I mean, these two S and T because you have the third row and the fourth row to be 0. Right? So number of those 0 rows indicate the number of freedom or number of dimension, okay, of your row, I mean null space. Okay? So previously I told you the number of leading ones will be the rank, right? And if the number of zeros indicate the you know the how should I say, like the freedom of the null space, then you know pretty much, because like the whole thing consists of this n. We have like a n component. This is like Rn, right? This is Rn, right? Okay, because this is n times n. This is n times n matrix, right? So you know, because of that, so the direct consequence will be the rank A plus nullity A will be n. Okay? Yeah, I mean, reduced row form, reduced echelon form, basically like, yeah, the similar argument. Okay. So far so good, right? I mean, you guys are still with me, right? 对不对？就是其实这个东西，你就是把它弄成那个 row echelon form， 你去看，其实蛮容易理解的。就是说，有时候你这个我们后面讲的这个东西，如果说你拿到前面去那个，虽然我们在第1章的时候讲的东西，好像是在解那个联立方程那个线性联立方程组嘛。However, okay, I mean the technique used there, okay, can be used to prove a lot of theorems, okay, I mean higher level theorems. Okay. So how about this? The solution of AX equal to B. If x0 is a solution of AX equal to B, then the solution set of AX equal to B is x0 plus x prime, where x prime comes from the null space. Okay? So that's this pretty much means like for a given solution, okay, you can expand that given solution, I mean, into like a lot of solutions, okay, for the same set of like linear equations, okay, 就是你如果说有给你一个解 ，OK， 给你这个线性方程组的解，那你现在假设你知道一个解，那假设你知道 null space 长什么样子，那你那个解就可以 span 出来很多的解，用这个 null space 里面的 vector。Okay, this is this proof is actually trivial. Okay, very easy. Okay, so if x0 is a solution of AX, so we know like A好像 let's try A x0 equal to 0, right? Because x0 is a solution for AX equal to 0, right? So we have that. So the solution set AX equal to B is x0 plus. So if you have like you know x prime, if you have x prime, okay, that is ax prime equal to 0. And then, okay, for any x, well, x double prime, okay, so if given for any x double prime, okay, such that a x double prime equal to b. So in other words, for any solution of ax equal to b, if ax double prime is the solution for ax equal to b, of course ax double prime equal to b, right? Okay, then we can represent x double prime equal to, okay, x prime plus x0. Okay, x prime, we can decompose it such that ax equal to x prime equal to 0 and ax0 equal to b. Okay, how do we get that? Okay, it's actually very simple, okay? Because we have this, right? Okay, and we don't have this. We haven't had this yet. So if we are given this, then we just let x prime to be, you know, x double prime, subtract, okay? You just move the x0 to the other side. Okay? To the other side. And then ax prime, okay, you apply a on both sides, equal to ax double prime minus x0 equal to ax double prime minus ax0, right? So this ax double prime, what is ax double prime? Ax double prime, we already know it's b, right? Okay. Wait a moment. Oh, sorry. X0 is the solution for ax equal to, so this is x. Sorry, I made a mistake. Okay, so x0 is the solution for this, right? Okay, so I made a small mistake there. Sorry about that. So this one is b as well. So b minus b equal to 0. So we know ax prime equal to 0, where x prime is this. So in other words, x double prime, any solution for ax equal to b can be decomposed into into x x prime and x0, where x0 is the solution for ax0 equal to b, one solution, and the x prime is like some vector in the null space. Okay. The last one for this section, okay. Ax equal to b is consistency if and only if rank A equal to rank A, no, bar B. Okay, so you just put the B as like a last column with the matrix A, right? Okay, so you consider this A bar B as if A is a n times n matrix, okay, then this A bar B will be n times n plus 1, right? Right? 因为你加了一个 row column 嘛，原来是 n times n 乘 n 的这个 matrix， 那你加了一个 column 进去，那这个 matrix 是 n 乘上 n 加1 ，right? So So here, okay, when we say consistency, okay, if these two ranks are the same, if these two ranks are the same, what does that mean? It means that, okay, 它们两个的 their like row space or column space are the same. Sorry, row space are the same. Let me correct myself. Their row space dimension are the same, and the column space dimension are the same, right? I mean, both were equal to rank A, right? So, in other words, okay, can I erase this? Okay, in other words, adding that one extra column into your matrix A, okay, in other words, adding that one extra column into the matrix A does not increase the rank, right? Okay, otherwise, I mean, they wouldn't be the same, right? They will not be the same. Okay, so adding this additional column at the end of the matrix A, okay, does not increase the dimension. So what does that mean? It means like if this is like a bunch of columns, and this is a B, this is a B. If adding this one, it does not increase the dimension, that means B can be formed by linear combination of these column vectors, right? Right? Let me repeat. Okay, 我再重复一次。如果加了这个 B, if I add this B column, it does not increase the dimension of the column vector, column space. Okay, it means this B actually can be formed by the linear combinations of all these column vectors, right? So in other words, okay, if that's the case, say B is x1 a1 plus x2 a2 plus plus xn an. That actually means what? That actually means ax equal to b, right? 对不对？你把 b 写成这些的线性组合，然后事实上这个东西按照这个定义，它们其实就是 ax 嘛。对，这个 x 就是 a1、x1、x2、x3，就是这些这个。那 a 大 A 就是这个小 a1、小 a2 这些 column vector 形成的 matrix， 对不对？按照定义。Okay. So the dimension of the column space, okay, are the same as that of A. So this implies the dimension of row space of A and A, bar B, okay, are also the same. In other words, rank A equal to rank AB. Okay, so basically, if you can obtain B by linear combination of these AIs, then you put the B as one additional column there. Okay, it does not increase your rank. Put it another way, okay, we call such thing as consistency. Okay, actually, what does that mean? That means AX equal to B has a solution, right? That means AX equal to B has a solution. I mean, here, okay, the way I do it, I do it from top to bottom, but I can obviously do it reverse. I mean, in a reverse order. If there's a solution here, then we have this, right? So in other words, I mean, if putting this one does not increase the column space dimension. Okay, so I mean, from top to the bottom or from bottom to the top, I mean, they are the same. So that's why, okay, We have an if and only if there. Okay? So far so good, right? 所以刚好这一章结束哦。That's the end of this chapter. Okay, so yeah, let's take 10 minutes break. When we come back, we'll continue. We'll start the next chapter. Okay? Yeah. Any question? Okay. I'll see you like in 10 minutes.